Hello, welcome to my channel. Welcome to Rehandran. In this video, I will talk about EMF 101. This is my second video on EMF essentials. So, in the previous video, we talked about the coordinate systems and their relationship with each other and what coordinate system transforms like when we transform from it looks like in different coordinate systems, and we will see some numerical problems. This is obviously Cartesian system, which is always uh, considered uh, as reference frame for convenience. This is the easiest of the coordinate systems, orthogonal coordinate systems. So here, so here x, y, and z are Cartesian coordinate variables. So x, y, z are Cartesian variables. Now on xy plane, rho, then phi equals this, and z, rho, phi, and z are cylindrical coordinate variables. Now r, theta, and phi are spherical variables. R, theta, and phi are spherical variables. Now if we see that if we see closely that r has scalar projection on xy plane, which gives rho, okay. Or r has vector projection, or on r has vector projection on xy plane. Now if we see like this, so this projection is rho, okay. This is the vector projection of r on z axis, which is rho. This is the scalar projection, which is z, which z is r cos theta. Rho is r sin theta. Y is rho sin phi, which is the vector projection of rho, okay. And y is the vector projection of rho on x-axis. uh, Here this is x is rho cos phi. So x is scalar projection of rho on x-axis. Now that we have say this point is P, okay. So P in Cartesian coordinate are x, y, z. P in Cartesian in cylindrical coordinate, P is rho phi z, and in spherical coordinate the same point P is r theta and rho. Say the point makes a vector with the origin A. So how can we define A on the three orthogonal coordinate systems? So A in uh, Cartesian system, A in Cartesian system gives component AX in the direction of X with unit vector AX plus we have seen this in the previous video. So a y component in the direction of y with unit vector a y a z with unit vector z in the direction of z. In cylindrical, it gives a rho in the direction of rho a rho plus a phi in the direction of phi a phi plus a z in the direction of z a z equals to in spherical, the vector which goes through the point P is like this: a r in the direction of ar plus a theta in the direction of a theta plus a phi direction of a phi. Now in terms of a full vector, if we want to transform a vector in Cartesian system to vector in cylindrical or spherical and vice versa, how would we do that? Now say we want to transform vector A in Cartesian to vector A in cylindrical form. Okay, so to do that, so let us first define the let us first define the vector in Cartesian: ax plus ay plus az. Now we know ax in cylindrical system, ax ay az in cylindrical system. If we just replace those, we will easily get the full vector in cylindrical system. Okay, so if we now trans if we replace this with ax, replace this with the value of ax in terms of cylindrical, so rho phi z, so ax has the component cos phi a rho minus sin phi in the direction of a phi plus ay sin phi a rho plus cos phi a phi, and az has az. Now let us uh, rearrange this. So let us rearrange in terms of arrow. Arrow has ax cos phi plus ay sin phi arrow plus ax minus sin phi plus ay cos phi a phi direction a phi and plus az, which can be written as a rho plus a phi in the direction a phi plus z, which can also be written now. A rho is ax cos phi plus ay sin phi, and a phi is minus ax sin phi plus ay cos phi. Okay, for uh, to for ourselves, let us draw the diagram. It will be easy for us to understand. So this is the cylindrical system with reference xyz variables, xyz coordinate axis. This is phi, a row, this is phi, so which gives, so say this is a vector, so which will give us the a phi is a row and this is az, the direction, which will give us the corresponding values of the component of the full vector. Okay, and az is az, it has no extra components, and that's that. If we convert a vector, a full vector in Cartesian into, so this is the conversion. If we uh, convert a full vector from Cartesian to cylindrical, the transformation will be like this. Now what will be the transformation vice versa? Say we are transforming a full vector x, y, z into vector in cylindrical rho phi z. So we have done one conversion from Cartesian to cylindrical. Now cylindrical to Cartesian, what will it look like? So say vector A in cylindrical form is a row plus a phi plus az in the direction az. Now to get the vector in Cartesian form, we just replace the value of a row in terms of a xyz, a phi in terms of xyz, and az in terms of xyz. So from earlier derivation, or from this we can easily find a row the components. So from earlier derivation or from this diagram, we can easily find the value of a row in terms of xyz, a in terms of unit vectors x, ax, ay, az. Okay, now a row ha has the components cos phi ax plus sin phi ay, doesn't have any az component because they are perpendicular to each other, and a phi has the components minus sin phi ax plus cos phi ay, and doesn't have any az component because they're perpendicular to each other also. So and az no extra component. If we rearrange this, we will get a row cos phi minus a phi sin phi ax plus say a row sin phi plus a phi cos phi ay and az. Now here ax plus ay plus az, where ax is a root cos phi minus phi sin phi, and ay is a row sin phi plus phi cos phi, and az is az. Now let us transform a vector in cylindrical to vector in spherical or vice versa. Okay, so say vector in cylindrical is a rho, the direction rho plus phi plus az. So let us first draw a diagram for our convenience. Now say this is the vector rho phi and theta. Now, and this is a, which is also r. So from this we can get a rho in terms of a r, a theta, and a phi, which uh, gives which here x, y, and z. Sin theta a r, then for a theta we get, for that if we rho z r theta, for a row we will get sin theta ar in the direction plus cos theta a theta, and a row is perpendicular to z, that's why no a sorry a theta, as a row is perpendicular to a phi, there's no a phi, so this is the uh, conversion. Now for a phi, which has the components, in this case a phi is a phi, there's no uh, extra component because a phi is perpendicular to ar and a theta. Okay, so there is no extra component. For az unit vector az has the components, this is um, cos theta ar minus sin theta a theta, and it has zero component in the a phi because a phi and az are perpendicular to each other than this. So we, for by rearranging, we can get a rho sin theta plus az cos theta AR, and we get, so for A theta we have the components A rho cos theta minus AZ sin theta A theta and A phi in the direction A phi, which gives AR AR A theta plus A phi, where AR is A rho sin theta plus AZ cos theta. A theta is A rho cos theta minus AZ sin theta, and Fi is Fi. This is the transformation of a vector in cylindrical to vector in spherical. Now for vice versa, now for uh, vector a vector A in spherical, if you transform it into a vector in cylindrical, it will be A theta Fi. Just put the value of AR in terms of rho phi z, which will give rho phi z, which will give from this. Here has the component rho is sin theta A rho. Now for phi is 0, and for z plus cos theta A z. A theta has to uh, put the value now for A theta, which is cos theta A rho minus sin theta A z, and A theta is perpendicular to A phi, so no component, and A phi is plus A phi direction A phi, which gives A r sin theta plus A theta cos theta A rho. This is here, this is A rho. Now Fi is just Fi, and for Az, A r cos theta minus A theta sin theta Az. This is, which will give A rho in the direction A rho plus A phi plus Az in the direction Az, where A rho is AR sin theta plus A theta cos theta, and A phi is A phi. Az has the components AR cos theta minus A theta sin theta. Now for the transformation of a vector in Cartesian to vector in spherical and vice versa, say A is X plus AY plus AZ. Now just put the value of a unit vector AX in terms of AR, A theta and A rho, so which will give us AX has the components. From previous video we have seen that AX has the components A sin theta cos phi in the direction AR plus cos theta cos phi a theta and minus sin phi a phi plus ay. The unit vector ay has the components in terms of uh, r theta phi is, or r components are sin theta sin phi ar plus cos theta sin phi a theta plus cos phi a phi, and az unit vector az has the components cos theta ar. So cos theta ar minus sin theta a theta. Now which will be a x sin theta cos phi plus ay sin theta sin phi plus az cos theta ar plus ax here cos theta cos phi plus ay cos theta sin phi and minus az sin theta a theta plus for phi here minus x sin phi plus ay cos phi, and no z, obviously phi is perpendicular to z, thus no component, and a phi now which is a r in the direction ar plus a theta in the direction a theta plus a phi in the direction of a phi. Now after the transformation we find ar equals to ax sin theta cos phi plus ay sin theta sin phi plus az cos theta. Ar is this in xyz in the component. Now a theta has ax cos theta cos phi plus ay cos theta sin phi minus az sin theta, and a phi has this minus ax sin phi plus ay cos phi. So for the vice versa transformation for spherical, a vector in spherical system to Cartesian system, let us first express that vector ar plus a theta plus a phi a phi. Now just put the value of a unit vectors. So ar, now ar unit vector ar has the component sin theta cos phi plus sin, okay, ax plus sin theta sin phi in the direction ay and cos theta in the direction AZ plus A theta. So A theta has cos theta cos phi in the direction X plus cos theta sin phi in the direction AY minus sin theta in the direction AZ plus A phi has minus sin phi AX plus cos phi AY. Rearranging this will give AR sin theta cos phi plus A theta cos theta cos phi minus A phi sin phi AX plus AR sin theta sin phi plus A theta cos theta sin phi plus A phi cos phi AY direction AY. Now for AZ, AR cos theta plus minus A theta sin theta. A phi doesn't have any component because they are perpendicular. AZ, which is AX plus AY plus AZ direction AZ. This is the transformation of the vector from spherical to Cartesian. We are gonna know about another topic, which is the distance between 2 points in a vector. So say this is P1 and this is P2. Okay, so what for the calculation of distance from P1 to P2, say distance D is here R2, this is R1, Y, X and Z. Okay, let me write it little here. Let me so the distance will be R2 minus R1 from vector. If you have no we know from vector that distance from R1 to R2 is R2 minus R1. So in Cartesian the distance will be like this: x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. In cylindrical it will be big, rho 2 square plus rho 1 square minus 2 rho 1 rho 2 cos phi 2 minus phi 1 plus z2 minus z1 square. In spherical it will be more larger, it will be larger. So r2 square plus r1 square minus 2 r2 r1 cos theta 2 cos theta 1 minus 2 r1 r2 sin theta 2 sin theta 1 cos phi 2 minus phi 1. That's it.